Thank you, and thank you for the invitation. So it's a joint work with Weiyong He from Oregon. So this is slightly different from the main theme of this conference. So we know the Kähler geometry study even-dimensional manifolds, and there's a less well-known all-dimensional analog called Sasaki geometry. So in Sasaki geometry in dimension 2m plus 1 is related to Kähler geometry in both dimension 2n and 2n plus 2. So it's somehow it lies in between. If we want to do induction for Kähler geometry, somehow we need to understand Sasaki geometry. So the standard example to understand this is the all-dimensional sphere. It's, on the one hand, it's the unit sphere in Cn plus 1, and on the other hand, it's fibers over Cpn. So there are lots of things in Kähler geometry which extends readily to Sasaki geometry, and so today I want to show an example where this all-dimensional Sasaki geometry can be used to give applications in the study of Kähler geometry. So let's first recall a well-known thing in Kähler geometry, the Frankel conjecture, or in algebraic geometry it's called the Hartshorne conjecture. One of the Hartshorne conjectures. So it says that a compact Kähler manifold with a positive bisectional curvature is bi-holomorphic to Cpn. So this notion of bisectional curvature, this star means any point. So my manifold is M, it's dimension n. If we take so we are we have a Kähler manifold, Kähler metric. So we take two tangent vectors non-zero in the complexified tangent space. Then the complexified remaining curvature tensor acts on U bar, V bar is positive. So this notion is so this positivity notion is weaker than the sectional curvature being positive. So I tend to understand this from the Riemannian geometrical point of view. That in Riemannian geometry, usually we want to study the relation between curvature and topology. So under certain curvature conditions, we know the topology of the Riemannian manifold. But the interesting thing about this is that for Kähler manifold, if we know something about curvature, then we not only know the topology but also the complex geometry of the Kähler manifold. So this is well known. It's not conjecture. It's proved by Mori and Mori-Siu-Yau independently, where the Mori proves this more general Hartshorne conjecture, which requires only the manifold have ample tangent bundle. So this notion implies the Griffiths positivity of the tangent bundle. So it's stronger. A priori, it's stronger than the ampleness. So Mori's proof is purely algebraic geometric. And the Siu-Yau's proof uses differential geometry. Using one of the ingredients is to construct holomorphic CP1s, which in algebra geometry called rational curves in the manifold. So both so the way to prove this, they both rely on constructing rational curves of low degree. So CP1 is characterized by that any point there's a line through it. So, and the standard classical characterization of Kobayashi Ochi, that if you have a Kähler manifold M, if there is a ample line bundle such that C1 of M is big or equal M plus 1 times C1 of L, then M is biholomorphic to Pn. So once one constructs this rational curves of low degree, then one can prove this and use this is basically by Riemann-Roch and Kodaira embedding theorem. So the Kodaira embedding is actually a biholomorphism. So in differential geometry, one tends to understand it in a more naive way. So we have a metric on the manifold, so we want to deform the metric to some canonical metric, and then using this canonical metric to conclude the property of the manifold itself. So this has been proposed by Yau a long time ago, using Ricci flow to reprove this theorem. And the key point is the metric characterization of Pn. So Goldberg, Kobayashi. So if we have positive bisectional curvature, plus Kähler-Einstein, then it's not only biholomorphic, but the metric is also isometric to the Fubini-Study metric, Pn. So this is the main maximum principal argument, which proves that under this condition, the holomorphic sectional curvature is constant. Then get the conclusion. So the naive approach is to deform any such metric to a Kähler-Einstein metric. So this is Ricci flow. It's normalized so that it stays in the first chain class of the manifold. So it's well known that because this is always a funnel, normalized Ricci flow always exists for all time. Exists for t 0 to infinity by Chau's theorem, and Mok proved that this I will denote it by positive to mean that it has a positive bisectional curvature. This is for all t. For all t. So this condition is actually preserved. And then before Perelman, there are results proving this convergence of this Ricci flow to the Fubini-Studium metric, but by assuming it's actually Pn. So that's work out for Chen Tian, and later by Fong, Stern, Song, Wankel. So what the argument says, even assuming this Frankel conjecture, this result actually is interesting in that we know all the space, any Kähler metric with a positive bisectional curvature can be deformed smoothly to the Fubini-Studium metric. So the moduli space of all such metrics is contractible. So this is not a priori. This is quite hard because this curvature tensor is quite nonlinear. So if one wants a direct proof, then one need to study this Ricci flow, and then by the deep theorem of Perelman, that in our setting, it says that the geometry of this sequence of metrics is uniformly bounded. So in particular, by taking a subsequence, this G, Ti, J, this Kähler metric converges up to diffeomorphism. So there are also a sequence of diffeomorphisms, so that it converges to G infinity, J infinity. So there are two problems. So first, this J infinity might in general be different from J. But then similar argument to Mok's shows that this also has a positive bisectional curvature. And using this, one can show there's no deformation of J infinity. So J infinity is actually J. But the more serious problem is that in the limit, we don't get a Kähler-Einstein necessary. The Perelman result only tells us that we get a Kähler-Ricci soliton. Where X is a homomorphic vector field. In particular, X is J gradient of a real function. So if one knows that this X is 0, then this will be Kähler-Einstein, and we are done. So, but in general, we don't know this a priori, and it turns out that if we don't restrict to manifold, but also consider orbifold, then actually we do get a non-trivial X in general. There's no Kähler-Einstein metric on a certain orbifold. So we cannot hope to directly prove this x to be 0. But the good thing that the x, the Jx is isometry. So Jx is a Kinning field. So it generates, it's contained in a maximal torus, a compact torus of isometries. It's a finite dimensional torus. So we are actually only finite dimensional away from being Kähler-Einstein. And then naively, we should think of a finite dimensional deformation after this Ricci flow, which is infinite dimensional object. So this is where we need the Sasaki geometry. So it seems that it's only finite dimensional difference away from Kähler geometry. So let's review basic Sasaki. So because of this picture, there are two equivalent descriptions of Sasaki structure in terms of both one-dimensional higher or one-dimensional lower Kähler manifold. So for us, let's just take this as a definition. Sasaki structure on all-dimensional manifold is a Kähler cone structure. On the cone x cm is m cross r plus. It's a cone. So by a Kähler cone structure, it's a Kähler structure. It's a J, G, such as a metric is a metric cone. So the metric can be written as a dr squared plus r squared gm. So this r coordinate corresponds to this radial direction, and we can identify m with the link r equals 1. So it's a Kähler manifold, which is also a metric cone, and then we get an induced structure on M. And this structure is called the Sasaki structure. And conversely, Sasaki structure gives you a Kähler cone. So the effect so first, because it's a Kähler cone, this Kähler metric has a very nice expression. It's dd bar of r squared. So it's r squared is global Kähler potential. We will use this later. When we deform Kähler cone metric, we deform this potential r squared. Second, r is we consider the radial vector field r ddr, and then we rotate it by j. So the r ddr is orthogonal to m. If we rotate, then on m it will be tangent to m. So this is a vector field on m. It's called the Reb field, Reb vector field. Yeah, we will view it either on the Kähler cone or on M. It's a Hamiltonian Kinning field. In particular, it preserves it's a holomorphic vector field. Preserves the whole Kähler structure. 3. there's the dual one form to psi, so eta is j of d log r. This is dual to psi, and this restricts to a contact one form. On M. So the Sasaki manifold is the contact manifold together with something like the complex structure. There's 4. It's a psi generates geodesics. Generates a geodesic foliation. It's called a rib foliation. So that then there's 3 types of Sasaki manifolds according to the behavior of this foliation. So first one, you can first classify either the orbits are closed or not closed. So when there is a non-closed orbit, it's not orbit, leaf of the foliation, then we call it irregular, and otherwise we call it quasi-regular. Otherwise, so in the quasi-regular case, this psi generates an S1 action, and then one can take a quotient of this S1 action, get a Kähler orbifold. And because we come from this Kähler cone, actually we get a polarized Kähler orbifold. So it comes from an ample line bundle over it. So then we call it regular when this S1 orbit all have the same length, so no exceptional orbit. So all orbits have same length. Then we get a polarized Kähler manifold. So the Kähler manifold together with the Kähler metric. So sorry. No, in this case also acts freely. You may get some orbit with longer with multiplicity. This is always free because this psi has a length 1. So it's always a free action. And on the conversely, it's also true. Given a Kähler manifold, we can take its S1. Given a polarized Kähler manifold, you can take the corresponding U1 bundle, and that will have a corresponding Sasaki structure. It sits inside the ML. Okay, this M P L. P is a Kähler manifold. L is an ample line bundle. Then one can look at the dual line bundle over the total space of a dual line bundle. One can contract the zero section, get a cone. If we have a Kähler metric, then there's this R will be the same as the length function defined on this total space. And similarly for the Kähler orbifold case. So still this example, standard example is this flat Cm plus 1 alpha in space. It's a flat metric. It's a standard complex structure. Then the corresponding potential function is just the norm square, sum of the norm square of the coordinates. The m r equals 1. This will be the standard unit sphere. And psi is the standard rotation vector field xi dd yi minus yi dd xi. And in this case, when take a quotient, we would get a CPN. So the quotient together with the Fubini-Studi metric. So this is the nicest case we have. And in the irregular case, usually we cannot take a global quotient, otherwise we get a non-Hausdorff space. But we can take a local quotient. So one can still talk about this for transverse Kähler geometry. And this transverse Kähler geometry is purely formal analog of the Kähler geometry, Euro-Kähler geometry, and it seems it might have nothing to do with the algebraicity, because in this case we actually get the algebraic stuff, but in this case, even it's not algebraic from the first view, but then the fact is that a Kähler cone is always an affine. It's always an affine variety with isolated singularity. So it's still algebraic in some sense. And together with torus action coming from this Riemann field. Right. So So from this, it's well known that Pn as a Kähler manifold has no deformation at all. But in a Sasaki case, it has deformations. So let's talk about deformation of Sasaki structures. Even for polarized Kähler manifold, we take its S1 bundle, we get a Sasaki manifold. Then we get more deformations than we can do in Kähler geometry. So let's first fix a Sasaki manifold M psi eta G as defined before. So we fix a torus action T so maximal torus in automorphism group. This is a space of isometries which preserves psi and eta. Take a maximal torus. This is the setting we have. So the problem with this Kähler resolution is that we cannot kill this homomorphic vector field. But now, if we have this vector field, then we get extra deformations. Now we only consider T invariant objects. So everything will be torus invariant, fixed torus. So the first thing is so the first is the analog of deformation within a Kähler class. So it's an analog of a Kähler class. This is called type 2 deformation. Yeah, I should say this deformation of Sasaki structures we use the description by Martelli-Sparks-Yau, and also that we use this Kähler cone description, but there's also description just using the transverse geometry by Boyer-Galitzky. So this name I got from Boyer-Galitzky, but this is a type 2, so it's less interesting deformation. So this deformation is preserves to fix the Reb field psi. So I should say that this deformation O and J, they both fix the complex structure on the Kähler cone. We fix the underlying complex variety. Now we also fix the Reb vector field. Then we want to deform the Kähler metric, deform the Kähler cone metric. That amounts to deform scalar potential R. So we need this condition to hold. Because Reb vector field is fixed, and this corresponds to R prime. It's R times a function phi, which is R invariant. Radial invariant function. And one can compute the deformation, the change of the Kähler metric, the transverse Kähler metric. So it's a local, this is a Kähler metric on the local quotient. Omega t prime is omega t plus dd bar of phi. And this is exactly what we get when we deform within a Kähler class. So when we fix the Reb field, it means we fix the underlying. If in a regular case, we just fix the Kähler manifold and deform metric. So from this, so this is maybe we should call it Sasaki class. So within this Sasaki class is a formal analog of Kähler class, and lots of Euro theory for Kähler class extends to Sasaki class. Like it's also known, it is non-positive curved infinite-dimensional symmetric space. And there are also study of geodesics, and so on. So for us, this is type 1, type 2 deformation is not enough. We need to obtain deformations which does not come from the deformation downstairs. So this is called type 1 deformation. Before this, we need to introduce a notion of rib cone. So this we define to be connected components of vectors psi prime in T, the Lie algebra of the torus T, which is a rubber vector field of Sasaki Kähler cone T invariant Sasaki structure. So we want to deform psi. Now we want to fix the complex. We want to deform the rubber vector field psi. But we want to know a priori which psi can we get to when we do this deformation. This is a rubber cone. So the lemma is that the C psi, the rubber cone of psi, is contains all psi prime such that eta act on pairing with psi prime is positive. This is similar to some Kähler cone. We deform Kähler class, but it's a bit different. There's also a deformation, an analog of Kähler cone, but it's different from this. There, the rubber field is still fixed. So from this, one imply that this is an open convex cone. But from the definition, it's not clear why it's a cone. And then type 1 deformation. So we want to deform the rubber field psi to a new rubber field of a Kähler cone metric. So the way to do it is just by solving ODE. So you can write down the equation psi prime. For any psi prime, you can try to solve this equation. But this ODE, we need to fix the boundary condition. So we fix the link 1. And then naively just solve this ODE. It's not clear. It does not have explicit solution, but one can study its asymptotic behavior. And this defines a Kähler cone metric exactly when psi prime defines. Calicone metric. Exactly when psi prime is in the wrap cone of psi. So this deformation on the link on M, the new eta prime will be simply eta over eta psi prime. Simply the contact structure still fixed. So one can understand these two deformations in that. So my understanding is that. So it's basically about. Yeah, I should say that this is still a fixed common structure J. Yeah, it's I should write J minus J. Yes, thank you. Yeah, you just simply multiply J on both sides of them. Yeah, to the underlying complex variety is still fixed. So type 2 deformation is sort of fixing the transverse holomorphic structure and deform the Kähler metric. And type 1 deformation is fixing the CR structure and deforming the metric. So in all-dimensional manifolds, there are two notions of complex structure. One is the CR. It's a transverse holomorphic. This is corresponding to view. We need a even dimensional subbundle or a even dimensional quotient bundle. So that's why we have this new deformation. We can fix the CR structure and change the underlying holomorphic structure, which means we no longer have the same Kähler manifold. Particularly, this psi can be irregular, so we actually have no quotient space. So the example. So I only have the example of sphere. So take again and we know there's a standard wrap field, and the wrap cone for this will be simply Rm plus m plus 1 plus. So it's all sigma ai psi I. It's a positive linear combination of the basic wrap vector field, basic Killing field. So standard one corresponding to all AIs being 1. So when AI is positive, we can always get a Kähler cone metric. And if A1, AN is proportional to a rational to an integer vector, then what we get is the weighted projected space. It's quasi-regular. And when lambda is this is the only case when the corresponding Sasaki manifold is quasi-regular. So all the others are irregular. So In this way, all weighted projective spaces of same dimension are connected to each other. It's like all rational numbers are connected by real numbers. So using this deformation theorem, I haven't stated what we have proved. All these are known, except probably the lemma. So we will use this deformation later, but the theorem we prove is that simply connected compact Sasaki manifold with a positive transverse bisectional curvature. So this name is quite long, but I don't know if there's a shorter name. But it basically means that the curvature of the local quotient is positive. Is a weighted Sasaki sphere. Right. So in general, we call such Sasaki manifolds a Sasaki sphere, weighted Sasaki sphere. Sorry? Yeah, it's to be more precise, it's a type 1. It's a deformation of the standard sphere via type 1 and type 2 deformations, or you can view it as a Kähler-Cone metric on this with a rubber field of this form. So from the proof, it's clear that the space of all such things is contractible. The modular space of all these matrix structures is contractible. And conversely, any weighted Sasaki sphere and any weighted Sasaki sphere admits such a matrix by a type 2 deformation. It means fix the rubber field, one can deform the Kähler potential to get a matrix with positive transverse bisectional curvature. The corollary of this is the corollary is so in a regular case, we can finish we can deal with the rich solution and prove this known theorem. And in the quasi-regular case, get some orbifold version of this conjecture. The proof is almost identical. We have to do this. The proof in the regular case cannot be too much simpler than the proof in the general case. But so in the general case, the classical proof seems to have some difficulties to extend to orbifold case. Yeah, this is all weighted project space. It's S1 bundle. That's called a polarized orbifold by Ross Thomas in their study of orbifold stability. Yeah, when I say Sasaki, it's a smooth Sasaki, of course. Yeah, probably. So I've been asking this question to algebraic geometers several times, but probably there should be some orbifold Hartshorne conjecture. Orbifold version of Hartshorne conjecture also, but which I don't know. Okay. So probably I don't have too much time to go over the proof of this theorem. Let me just mention the idea of the proof. Is again a similar theorem as to Goldberg-Kobayashi, that if the transverse bisectional curvature is positive plus the Sasaki-Einstein is also sphere with a round metric. We assume simply can get 1. So let me just say, continue the proof in the regular case. So we get this Keller-Ritchie-Soliton. Then we look at this S1 bundle. Then it will be a Sasaki-Ritchie-Soliton. Then one wants to deform this to a Sasaki-Einstein. And the strategy is to find a canonical deformation. For this, we need to use again the beautiful idea of Martelli-Sparks-Yau. That's the volume functional. That's a function defined on the rubber cone. So you take any Sasaki field, Sasaki manifold, you can compute this volume. In the Kähler case, the volume only depends on the Kähler class. In the Sasaki case, it only depends on the rubber field. So it's a function on the rubber field. And then they show this volume coincides with the Einstein-Hilbert functional up to some factor. And so for rubber field, for Sasaki structure to be Sasaki-Einstein, it must be a critical point of the volume functional. So they compute the gradient of volume functional. And this is exactly the Futaki invariant. So this is a map from T. And moreover, you know that the volume is strictly convex. So, yeah, so Sasaki-Einstein is a Sasaki-Ritchie-Soliton with the Futaki 0. So the natural way is deform it to a critical point along the gradient flow of volume function, and it's strictly convex. So similar to Joe's talk yesterday, for convex function, the gradient flow should behave nicely. So the strategy is to deform the rubber field along the gradient of volume function. But we also want to be and deform corresponding Sasaki-Ricci soliton. So it's not a purely, one can write down the gradient flow for the rubber vector field. That's no problem. But then one still need to be able to deform the soliton, which in general, when we deform spectral metrics, we make it singularities in general. And the key is to bound the geometry along of the Sasaki-Ricci soliton along this flow. So this flow is finite dimensional, and indeed we can show that the volume function is a proper function. So indeed there is a priori critical point in general. No, it's the properness is in general. Yeah, we just studied the boundary of this cone. Show this is proper. But even that we don't know how to deform the soliton. We can use the implicit function to deform for a short time, but for a long time we don't know yet. So we still need to go to bound the geometry, and for this there's a long calculation to show that the Perelman's mu entropy is increasing. Ft gradient Ft squared, and this is key. It's similar to the use of Perelman's estimate in the Keller-Ricci flow. This implies scalar curvature bound and the volume bound below, non-collapsing. So then the rest should be pretty standard. So this is so even in the regular case, we still need to go through this procedure and conclude we can get the Sasaki-Einstein and then go back to show the original. The thing is that we are always in a T invariant. So we fix the maximal torus, and then one can solve the Keller using implicit function theorem to deform it a bit. It might be unique, but it's unique up to isomorphism. So geometry is the same. This openness is by implicit function theorem, and closeness is by a priori estimate, which requires bounded geometry found in the curvature of these solitons. So this is the key, and this is really a lot. We still don't understand why it's true. Okay, thank you. Yeah, even hypercortex, I think differential geometry, we don't know much about its. How do I say? This really depends on whether one has a metric geometric characterization of. So for hypersurface, you have too many. You don't know whether they have good shape or you don't know even if they have Klein-Einstein metric.